A lot of debuggers have a UI. You have a debugger UI in your JetBrains IDE or VS Code IDE, and NeoVim has a UI too. And let me show that to you. I would need to set a breakpoint right here, and I can set a breakpoint with space BB, and that sets a breakpoint. You can see it right here, and space BR, and oh sorry, let's choose the command. Enter. So you can see this is the UI for the debugger. Anyways, we don't need the debugger right now. I did that for debugging purposes. I integrated a debugger in my new Vim, but we don't need it right now. I just wanted to show you what debugger UI is. And the UI captures and shows all the prints and logs to you. And it shows them to you even if you were writing them to the standard output. If you were to print line to the standard output, the debugger UI is able to capture that and show that to you. Since the process was being managed by the debugger, the process that we are trying to debug is being managed by it, we want a way to allow the debugger to capture that output, and we want a way to be able to show it to the users. And so we want for any process that we launch through our debugger, and we want our debugger to intercept its output and capture and process the output. And we want that to happen even if the process is writing to the standard output. So we'll update the launch function. We have the launch function right here. Launch. Let's go here and let's go GD. So we have a launch function right here, right? We'll update this launch function to accept a parameter. And that input parameter will be a file descriptor. That file descriptor will point to whatever output stream we want to direct the output to. So if we don't want to write to the standard output and we want to write to some file or some other output stream, we can pass the file descriptor of that output stream into the launch function, and we will replace the standard output with that file descriptor. So for now we will just pass it in a none because we're not building a UI. We launch our processes through cargo run, and then we pass it in the process ID that we are trying to debug. If you want to build a UI, you can update that startup API to accept a file descriptor, and you can use that to replace the standard output in this launch function. I will show how to do that, but we're not building a UI. So what we will do is we will pass in just a none for our case, and I guess that should work. We're building a CLI, and so I'll leave that up to you guys. But before we begin with anything, we will add two dependencies to our project, and we will use them shortly. Let me just add them. So the first is libc, and this libc will be used for a syscall that will be used to replace the standard output with the file descriptor that the user will be passing in. So 2 dot when preparing for this video I was using 177, so let's just use that. And then num traits, and num traits, let's just use the latest. So num traits, we'll use num traits as well later on. We'll get to that soon enough, but just add these two dependencies to your package. And I hope it's let me increase the size a bit. Anyways, that's all the dependencies that you want. Let's try to do a cargo clean and a cargo build. And before we update the launch function, I want to actually update Before that, before we update the launch function, I want to actually clean up the main function. So in the main function, where we have this, we are reading all registers and we are printing it. We don't really need that, do we? So instead of printing the user, what I'll do is gd read all registers. So it returns a result right here, but we're not actually capturing that. So let me do that. Let res equal to, and if let error equal to res, in that case I will print line, and I will just say, and we will return, we will not actually debug. If the result was not an error, only in that case will we call this debug function. So we wanted to clean this, and we have this same issue actually somewhere else as well. We have it in the wait on signal function. So we have cluttered that. We did that for debugging purposes, but we don't really need that in the final out the final project. So let me remove that. Wait on signal function, wait on signal. You see, we have a lot of read all registers, print users. We don't actually need that. So let's remove that. Let's remove this, and we'll do the same thing we did in the main function. Uh, let res equal to this, and if let error of e equal to rel, in that case I will print line, and I'll just print out the error. All right, and we don't need this print user, do we? I don't want to print any, I don't want to print, yeah, don't really need that. So now we finally want to update the launch function. So let's go to that. Launch. Yeah. In the launch function, I told you that we're going to accept a parameter, an extra parameter, and let's just call it. And this parameter I will actually be used to replace the standard output. So let's call it standard out replacement, and it will be an option because we are going to pass it a none for now, and it will be an option of raw fd, and that's the parameter that we want to accept. We're not using it right now, but let's accept that. And with this we will need to update our wherever we are using this launch function, right? So launch, where are we using this? We are using it in attach.rs, and for now I told you we will be passing it a none, and we also need to update it in the test intake tests. So space fw test process launch. So test process launch, are we calling? Yeah, we're using a launch here. So let's just pass in a none, and where else? Launch, where else? Here, let's pass in another none. All right, and with that we should be able to do a cargo clean and build. So Let's do a cargo build. Oh, okay, status. It's in process. So line number 189. And when line number, if ePrint line otherwise okay of status, cannot find value un in this scope. What do you mean? Oh shit, my bad, guys. So the build worked fine. Okay, so let's get to actually replacing the standard output in the launch function. This replacement needs to happen in the child process. So right here in the child process, we want to duplicate the standard output to whatever the file descriptor was given to us. So oh, hmm. So if we have some file descriptor, sum of FD in the standard output replacement, if there is some FD given to us and it's not none, what we will do is, if we'll use the libc crate that I told you, and libc of dupe2, this takes a file descriptor, and the so this is the file descriptor we want to duplicate to, and we are duplicating the standard output, and libc provides that to us. Std out file number, and this returns a 0 if this returns a negative number in case there is an error. So we will panic in that case, and I'll say standard out replacement failed. That's it. So this libc function will actually do the replacement of the file descriptor from standard output to the file descriptor that we have passed in. So anything you write to the standard output in the debuggy process will be returned to the file descriptor that was given to the debugger. And let's just make sure all the imports are done fine. So we have the raw FD and libc. We are importing we're using libc directly. Unused imports. So yeah, we are actually not using these. So let's remove them. Let's write and let's do another cargo build. Cargo build worked fine. All right. So to do some manual testing, we will add some commands to our CLI. So right now our CLI only has the continue thing. So if you press C or type out continue, that will continue the process. Otherwise the process would have been halted. As soon as we press continue, that's like the go button in your debugger. So we'll add a few other commands to our CLI, and those commands will allow us to read and write values to registers. So we have the command handler in process.rs file. We have the dispatch command function, right? So we'll update that space ff. So we are in process. So we have the dispatch command right here. Okay, so the dispatch command, and since we are reading and since now we are going to be reading and writing, that process is actually unsafe in Rust. So we will need to mark it as unsafe. It's not unsafe right now, but soon it will be. Anyways, like we are checking for the continue word, the continue command right here, we'll add other checks as well. So we will add a check for the help command, and this will give print out the menu for the debugger. If help dot starts with, and it will be the command. In that case, I want to create another function that will do that, handle help, and we'll pass in the args to it. Now similarly, else if register dot starts with command, then we'll create a self dot handle register, and we'll pass in the args right here. Okay, now we want to create these two functions in self. So let's write this much, and of course it won't work. Handle help found for no method named handle help, so we'll need to create that. So fn handle help, and it will accept args. Now args is a vec of string, right? You can see that right here, so we need to accept that. But since we're calling it with self, so it also takes a reference to self. So self comma args, which is a vec of strings. All right, and we also want another function func. So we'll do that later. Let's go function by function. So what I'll do is let's print line a large text so that we clearly know we have a clear demarcation. And then if args dot oops if args dot len happens to be equal to 1, we will print out all the commands that we have. So print line, I'll say available commands are, and let's just yank it. One y p available commands, and we'll say available commands are, let's give it a tab and continue resume the debuggy. I guess that's the spelling. Correct me if I'm wrong in the comments. And I want the other command we are going to have is the register command. So register and commands for reading and writing to registers. Reading and writing to registers, because those are the only two operations we're going to support for now. But if rx.length is greater than, if it's not equal to 1, then let command be equal to args of 1, and if register dot starts with the command, in that case we'll say print line, and I'll say available subcommands for command register is available subcommands are going to be huh, 1 by, and then available subcommands are going to be, let's remove all this. The commands you're going to support for reading and writing are read, so that is going to be 1. Then we're going to have read a particular register, so we'll take the register ID, read register, and we're also going to have a command that will read all the registers, read all, and we're going to have another command that will be for writing. So write, it takes the register ID and the value. But if that is not the case, if it doesn't start with the register, the only other possible command is continue. That has been taken care of. So if we get here, we can print that this is an unsupported command. If it's not register, it's unsupported right now. We'll add commands later on. Unsupported command, and let's just print what the command you gave us was. So that is the handle help function, but we also now need the handle register function. So we want to handle all these commands, the read, read register, read all, and the write register command. So let's create that now. Function, and it's going to be an unsafe function. So unsafe fn handle register, and it will take a reference to self and args, which is a vec of str, and in here if args.len is less than 2, we'll call self. So if you give us only register, but register is no command, register must be followed by a subcommand like read or write. So if it's just register command, then we are going to call the handle help again and tell the user that you're calling the register command incorrectly. Handle help, and we'll pass in the args, and then I can return because we need a sub command as well. So let sub command equal to args of 1. Is it 1 or does it need to be 2? So help will be 1. Help and then register. Okay, so sub command will be 1. Okay, so 0 will be register and then 1 will be read or write. So sub command, this will be read or write. Args of 1, and this will be equal to read or write. And so if read dot starts with sub command, if that is the case, we'll call self dot handle register read, and we'll pass in the args. We'll create another function. Else if write dot starts with sub command, in that case we'll call self dot handle register write, which we will create shortly. And let's pass in the args, and otherwise I can say let command equal to register. You came here where command was register, and we'll say unsupported commands. So print line unsupported command, and I'll say this command comma subcommand. All right, so now we need to create this read and write functions. Formatting specifier missing. Okay. There should be two errors right now. Two missing functions, handle register read and handle register write. So let's create them now. We'll start with the read function. All right, so this is again going to be unsafe fn handle register read, and it's going to take self and then args again, which is just a vec of str. Maybe I should be copy pasting this stuff. This is quite boring, but anyways, if args dot len is equal to 2, so if you call read or read all, we'll treat those both commands as the same thing. So if args.len is equal to 2, or args.len is equal to 3, and the third thing is actually all args of 2 is equal to all, in that case we will read all the registers and we'll print them. So let res equals to, we did that earlier as well, we cleaned that code, so it's just the same thing. We'll read all registers, and if let in this reading, if we happen to find an error, we will return, but otherwise we'll print them. So print line, and in here I'll say e and return. But if there was no error, let's just print it self dot proc So when we do read all registers, that will store it in proc registers, and we can print that proc registers because we have created a function that prints it. So let's use that proc registers dot uh, data dot print user. All right. Uh, else if args.len happens to be 3, and if the args.length happens to be 3, the third thing, it cannot be all because we have handled that case already, so it needs to be a register ID. So we will treat the third thing, the index 2 thing, as the register ID, and we'll try to find a register by that, or it's can be a register name. Let's keep it a name for now. So we will pass in names like rax, ex, etc. So we'll try to find a register by that name, and if we don't find a register by that name, we should return and say that you gave us an invalid register name. So let register equal to register by we have a name, and let's pass in args of 2 does take it takes a string slice, so that should work. That will be the register, and it returns a result, right? It returns an option. Oh, so it's going to be an option. So if it is none, so if let none equal to the register, in that case, we'll say that you gave us an invalid name. Invalid register name, and I'll print the name that you gave to us. Args of 2, and we can return. Look. Otherwise, we have the register. So let register equal to register dot unwrap. This unwrap is safe because we've already checked for none. So now again we will read all the registers, and then we'll print a specific register. So let me copy these lines actually. That's about 1, 2, 3, 4, 5 lines. So 5 and then P. So we read all the registers. We check if we read them successfully. If we didn't, we return. Otherwise, if we did read them successfully, I can fetch the value. Let val equal to. So this read all register is what it does is it reads that from the actual memory register into our debuggers, that struct that we created. So self dot proc registers, we have a get register val by id, right? So get register val by id, we created this earlier, and we have the register. So register dot id, yeah, we can fetch the value by id. So what does this return? Call to unsafe function is unsafe. Our function is also unsafe, so shut up. It returns a result. So if this returns an error, if let error e equal to of val, if there was an error, we'll print what the error was, print line and then we'll return. But in case we got that value successfully, let val equal to val dot, we can unwrap. This unwrap is safe actually, and then we can finally print the value. So we'll print the register name and the value. So let's add about 3 tabs, and then args of to and val, that will print the register name and the value. So we do this when we have the register name, so like read register name. But if the last thing, if the register length is greater than 3, what happens then? If it is greater than 3, then it's an invalid command. So we'll say in unsupported command. Print line, and we'll say unsupported command. So control will come here when args.length will be greater than 3. So we'll say that you have given us an incorrect command. And to tell the user how to use the debugger, we'll print the help menu. So that happens with handle help, and we can return from here. So that is the read function. We're calling an unsafe function here. Cannot borrow self as mutable as it is behind a reference. Read is mutable. It takes mutable. Okay, so it needs to be, yeah, because it's writing in a, so here it should be mute. The error go away? Yeah. What's the error? The error is there is no method name hand. Consider wrapping the function in unsafe. Which unsafe is there already? What's wrong with the LSP? Is there some config that we can change for the LSP? Let me know, guys, if you know. Not sure. This is giving me a lot of warnings that I should put unsafe right here. But unsafe works right here as well, right? Compiles fine. So how can I change that? I'm not sure. That it should recognize that unsafe is already there. Anyways, if you know, please let me know down in the comments. So handle, it doesn't look good to me. Make it handle register right. So we need to create this handle register right function. Okay, so let's create that. It's again going to be unsafe fn handle register right, and this is definitely going to take a mutable of self, mute of self, and it takes args, which is just a vec of str. So the register write command, it's going to take a register name and a value. So so the length of the args needs to be 4. Register write, register name and value. So the args dot length, if it's not equal to 4, then we tell them that they have given an incorrect command, and then we return. We don't actually process anything. So if args dot len is not equal to 4, in that case we print line unsupported command. So if args.length, but it needs to be at least 2, because read register write, so at least 2 there will be. Only then will control come here. So args of 0 is safe and args of 1 is safe. Aha. unsupported command, and then we can do self dot handle help to tell them that they have called it incorrectly, they need to correct their command, and then return. In the right, again we will fetch the register by the name. Let register equal to register by name, and then we give it args of 2, and then we can maybe copy from here, copy 3 lines, 3 and then I paste them here, and I can remove this. So if the register is none, we say invalid register name and then we return. Otherwise I can unwrap it. Dot unwrap, and then I can, so the value they are giving us will be a string. So right here args of 3 is going to be a string, but we need to parse it to a double or a int or a vector depending on the type of register we are writing to. So if the register it stores a vector, we need to parse the value, the args of 3 to a vector, and if it's the register stores a double, then we need to parse the string into a double, and if it stores a long double, then we need to parse it to the long double that we will be basically be using array of bytes for long double. And if it's an integer, we can simply parse, we can do a simple cast from string, parse from string to int. So we need a helper function for that, and we need a helper function to parse a value, and that parsing is going to depend on the type of register. So what we will do is we'll create that parse value helper function in the register itself. So because the type we are going to parse into depends on the register, so we'll have all that information about the register in the register self. So we'll create a parse underscore value, and to it we will send an args of 3. Now we do not have this parse value function yet, but we will create that shortly. And let's say it returns a result. All right, it's going to return a result. So I can, if it's going to return a result, I can check if we were able to parse successfully. If not, it will be an error. And if it is an error, I will print line the error. And then I can return and not actually process and update the register. But in case there was no error, let value equal to value dot unwrap, and then we created this function that updates a register by the register ID. So let res, and so this value is essentially going to be register value. This is the data type that I want because this function takes that, right? So let me check. Let res equal to self dot write to user by register ID. There it is. So as you can see, it takes a register ID and a register value. So the data type of this value right here is going to be register value, and this function parse value needs to return a result over a register value and a string for the error. So we'll call this, and we'll pass in the register ID, register dot ID, and the value. And what does this return? GD, what does it return? It doesn't return anything. Okay, so maybe I should return a result from here. So we will update it to return a result, because then only then will I know if we are actually correctly writing to the register, because we need to let that function know. So I'll update this function as well to return a result, and I'll check that right here. Oh shit, where was I? Right here. Arre? So if let error of equal to res, in that case I will print line, and all right, I'll print line. And what does this function return? We don't return anything from here, so that's fine, I guess. All right, so yeah, because we need to return a result, but we'll update that later. And since this, so that will be the register, right? So right now what we need to do is create this parse value function and update this register ID, write to user by register ID to return a result. Those are the two things we need to do. But we are calling this dispatch command function. This is we made it unsafe, and we are actually using it in the debug function. If you go there, as you can see, we are using that right here. So what we should do is actually make this unsafe, because the dispatch function is actually unsafe. So this should be unsafe as well. Had we did a cargo build, we would have seen that as an error. So right now we need to do two things. We need to create this parse value function. Also, we need to do sorry, we need to create this parse value function. So let's do that. Let's go to register and create this parse value function. So we have this register info, right? We go to register info, and inside here we have impl register by name. And what we can do here is create another function. This will be the pub fn parse value function. Parse value, and it takes a string slice. It takes a string slice. So it takes self and a string slice. It's going to take a self and a string slice. Self because I need to know the register info. Self and a string slice, and the string slice is basically with the value string, and it's going to be a string slice. But it needs to return something also, right? It's returning a result of register value. So let's go there. It's going to return a result over register value, and for error we'll use a string slice. All right, and now I told you this parsing is actually going to depend on let's make sure this register value is imported as well. So let's go up, 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 bruh. We don't have that. Uh-huh. So let's import that as well. So use a crate of RDB of process registers of register value. These are the only two places it's being used. So in here, the parsing we are going to do is going to depend on the type of register we are working with. So we need to match on self.register format, and this will tell us what we are working with. So if the register format, it happens to be a uint, uh, in that case the uints for us are of 4 different sizes. So 1 byte, 2 byte, 4 byte, 8 bytes. So we need to parse it accordingly. So we'll also do a match on self dot register self dot sorry size self dot size. And so if the size happens to be 1, we need to do something, and if it happens to be 2, we need to do something. If it happens to be 4, we need to do something. If it happens to be 8, we need to do something else. And in all other cases, let's handle that first. We need 1, 2, 4, 8. And in all other cases, I want to return an error invalid format. Matter of fact, I want to panic here because this should never be the case because we're matching on self dots. But anyways, you can maybe get away with a panic here because this should never be the case. The control should never come here. But in case we have this, what we want to do is I want to create an int out of this string. I want to create an int out of strings. So we'll create a helper function uh, that will be generic because we'll use it for all these 4 cases. And that helper function will take a data type for the generic. So it will be U8, U16, U32, or U64. And we will accordingly then create the uh, object of that data type. So I want to, let's me remove str. I'll create this function str to int, and let's say it takes a generic. So right here I'm going to give it a generic of U8, and it takes the valster, and it takes the, so we'll tell the user to give the string should be base 16. So since you are working with registers and all of that stuff is hex code anyways, so let's say we are working with base 16. So the user needs to give us a base 16 value. And if you don't want to work with base 16, you can take an extra parameter which can be base decimal 10 or something like that, and you can work on those bases. But let's say our CLI only accepts a base 16 for numbers. So in that case, let's give it a 16 right here. And if you want to do something else, you want to do a base of 10, you can update that. But I'll be using 16. And register, I want to create a, so what we will do, what this function will do is it will return a U8 to me. And when it returns a U8, I can create a register value out of it by simply mapping to register U8 like so. Hmm. We can do this. And if all of this works fine, if that string to int function doesn't cause an error, and if this map doesn't cause an error, in that case we'll do an okay. But Otherwise, I want to return an error, and this ok.or will help us do that. Invalid format. I can say invalid format. If it was okay, then okay. Otherwise, I'll say invalid format. So 3yy and then p 2 4 and then 8. So let me remove these and let me make them 2 4 and 8. So when we have 2, we are working with U16s, and in that case I want to create a U16. And in case of 4 we have U32, and I want to create a U32. And right here make it U64. Similarly make it U64 as well. All right, so that will be the uint case. In case of uint we will do this, but if we don't have uint, I will if we don't have u, the other cases are register format of double float, the next case is register format of long double, and the other is vector, register format of vector. These are all the possible values. So we'll update this later. Let me first create this str2 int function. Alright, let me create this str2 int function. So this will be this will be a helper function, right? So we can keep it outside of the impl block. Let's make it a function not associated with any struct. So fn str2 int, and as I said, it's going to take a generic. It takes a value stir, which is basically a string slice, right? And I said it's going to take a base, and since because we are working with base 16, and it can be updated to 10 if you guys want to work with base 10s. Basically the input, if you want the input to be in base 16 versus base 10, I'll show that to you. I'll show you how this CLI works at the end of the video. In the end of the video, we will test it, and I'll show you what I mean by base 16 right there. So basically the input that we're going to give to our CLI, it's going to be in base 16 format, like 0xFFF and 0x3FF, like that, base 16 format basically. So let me create this. So it's going to return an option of t itself, whatever whatever the data type we gave to it. And we want to, I forgot what they call it. Basically we want to add some constraints to this generic. I forgot what this is called in Rust. Basically, if you want to apply some constraints to this t, like this t should not be a string, it should not be a null or something like that. In that case, you can specify that like so. You can tell that here t should be a number, and this is where that crate that I added it comes in. I want to tell it that this t basically should be a number, and we are only working with numbers. That's basically what this does. You can probably get away with this as well. You don't actually need it, but this is good because we don't want this function to be called where t is a string or something. We don't want to parse to a string, right? So, uh, huh. So if the base is 16, which is the default case, In that case, the string will start with a 0 and x. Basically, we can strip that. We don't actually need that. All right. So if base equal to 16 and s dot starts with uh, 0 and x, 0 and x. In that case, I want to strip the first two characters from the string. So let's create another slice out of it, and I'll create a slice from index 2 onwards. We'll update. Let's say it returns that. Let s equal to this. Otherwise, s, like if you call this function with base 10, you don't need to strip anything, right? If you so if you for some reason you want to work in base 2 binaries, that's up to you, but in that case it will be starting with a 0b. In that case also you should be stripping 2, but we'll basically be working with base 16, so our control will always come here. We'll strip the 0 and x from the input and create a new s. Basically I want to call this call our CLI with a value like 0xff, that a b c d e f. F is like 16, right? So 16 16, so this is a base 16 number. So this is what we want. This is what I want to call my CLI with. I don't want to work with base 10 integers or something like that, because basically debuggers, they work on register values, and all the register values happen to be hex, so we should be comfortable with working with hex. And after we have this, so whatever data type you pass into it, all those data types already have a function that can be used to parse strings to that number. Like in Java, you would have integer dot parse int, double dot float double, double parse double. So like that in Rust, you have, since we constrained it to be a number, we can check the functions that will be there in it. So we have this function called from strradix, and given the string that is basically s, and the radix being the base, this should convert the string to the appropriate number. And then I can say dot OK, and that will create a option out of it. And since we are returning options, so that is it for str to int. Now we need to work. Now we need to handle all these double floats, long double, and vectors. So float is going to be simple. Let's do that first then. Uh, Double float is basically just like an integer. I mean the data type that we are working with is f64. We don't have we don't have f32 here, right? We have long double, but that is x87 10 bytes. So we'll have to write some custom logic to do that. We'll do that, but let's first handle this double float. So in case of double float, uh-huh. In case of double float, what I will do is I will do an str. I'll create another function called str to float, and let's give it a data type of f64. Let's use the data type thing we are doing so far and pass in the string. So similarly, similar to above, we will map and create a register value out of it. Register value of double, that is fine. Otherwise we'll say invalid format, basically. Invalid format. Now we should create this str to float function. So let's do that. Fn str to float, and this str to float, it also takes a generic, and that generic, so let's say the generic is f. It takes a string and we return an option of that f itself. So if we tell the Rust compiler that this f is going to be basically a flow, I mean, if we tell the Rust compiler that this f is going to have a function to parse a float, basically, I don't think we even need this, do we? Let me do something. Uh, we have the val stir. So val stir should have a parse function. Yes, it does. And this parse, it takes a generic num trait. It does take a generic. So let's give it f64. Takes an f64, and this should parse it to an f64. And let's just say okay. Syntax error, expected comma. So we don't need this function, right? No, we don't. It's a one liner itself. So what we're doing is we're parsing the string to an f64, and then we are saying we are okay, because I want to. So let's not do that either. What I'll do is I'll do a register, but it may be an error, right? So what does this parse return? From star, it returns a result. It returns a result. Okay. So I can say that it's okay, and then map double over it. But if it's not okay, so I need this okay because I want to map. So otherwise you'll have to write some ifs. I don't want to do that. So so what we're doing is we are doing a string dot parse. We are parsing it to f64. Then we are saying that it's okay, and then we are mapping, and this okay will create an option of f64. Then we are mapping, we're calling the dot map function to create a register value of double variant of the enum. And if any of the above functions caused an error, the okay or will be invoked right here, and it will return an error of invalid format. LSP look, quit it. So that's it for float. Now we have two cases left. One is vector and the other is long double. Let's handle vector first because it wouldn't. So vector is quite simple. It doesn't require us to do some custom byte manipulation. It's just basically a list. I'll tell you. So let's come here. And in here, what we'll do is vectors again are of two types. Uh, the types are based on the categorized on the size. So we have two types of vectors. One is of size 8, one is of size 16. Different registers have different sizes. I forgot which one exactly. I guess MMX, MMO, and XMMO. XMMO would be 16, MM0 would be 8, I suppose. Multimedia registers. I don't remember exactly, but I think that is the case. But anyways, so the two cases are 8 Then we are going to have other case will be 16, and in any other case here again you can panic. I'm just going to return an error, and let's just say invalid format. So in case of 8, what I want to do is I want to create a vector out of this. All right, so I'll create another function. I'll call it vector str to vector, and it will again be generic, and this generic can actually be a value as well. So the value will pass it in as 8. All right, and then we'll pass it the string. Now again, the way we have been doing stuff, we're going to is going to return an option of vector, and then what we're going to do, we're going to create map it to a register value of byte 64, uh, dot okay, or if it's not okay, we are just going to say invalid format, invalid format, invalid format. And we're going to do the same thing, but instead of 8 and 64 it will be 16 and 128. So str to vector, and instead of 8 it's going to be 16. It's visual mode, yanked. Let's remove these two lines. Make it 16, make this 16, and instead of 64 make this one 28, and 1 p. Okay, these are the two types of vector. One is byte 64, the other is byte 128. Basically how many bytes large it's going to be. So let's create this function str to vector, and we will use this number that we are passing to determine the to create a list of that long a list, and then we'll update the values in it. So basically for vectors, what I want to do is that I want my CLI to allow this type of value. So for here, uh, this is what the user will give the CLI. So user will give a command register write, and then it will say mm0, and then this. All of this will be accepted as a string, and then I want to parse it into an array of bytes. All right. So this needs to be parsed into an array of bytes, array bytes, array bytes. And so we want to create a vector out of it. So each of these individual elements need to be converted to ints, and then we'll create a list and we'll return that from here. And for this, for example, again, this again is going to accept an array of hexadecimal ints, and we need to we need to parse them. So let's do that. Let's create this str2 vector function, fn str2 vector, and this str2 vector, it also takes a generic, but this generic is basically a number. So we can tell the Rust compiler that it's going to be a constant, it's not going to change, and it's basically a usize. The data type of this is usize, and it accepts string slice, right? And I told you it's going to return an array of bytes. So option of uh, so an array of bytes, and that array is going to be n large, it's going to have n numbers in it. So each of those will be converted to bytes, and then we'll put them at the correct indexes. So what we'll do is we will, to start with, we'll create a array, and it will be filled of it will be full of zeros. So 0 of u8 and 0 of u8, and it's going to have n of these. This will create an array of bytes for us, and we have this string, right? So let's get an iterator over it. Let mute chars equals to s dot chars and dot peekable. This peekable returns an iterator. So what we can check now is, so this string will look something like this, right? So it must start with a square brace and end with a square brace. So we'll check with, for the starting square brace, chars dot next, if it is there, and if it is not equal to opening square brace, in that case we'll return a none. Return a none. Otherwise, what we will do is we will iterate from 0 to n, because we want to update all those right here in this array at those indexes. So for I in 0 to n, let hex str be equal to chars. So I want to take 4 characters. To do that, we can do dot by ref dot take 4, and then we can collect them to a string. But for this to work correctly, we need to tell the compiler what we are collecting to, and that we can tell by the data type right here. When we have, this will give me something like 0x12 or something like that. This will do that. This will give me a string. Now this string needs to be converted to a byte, and needs to be put into this bytes array at index I. So we already have a function that does that for us, str to int, and bytes of I equal to str to int, and I want to create a u8 out of it. So u8, and then I call the hex string. And if you remember, we are removing the first 2 characters with that function right here. If we start with, we remove the first 2 characters. So we pass in the hex string, and then we give it the base 16. This will create a byte for me. And now if the next character happens to be a closing brace, if it happens to be a closing brace, we're done processing, right? So we'll match chars dot next dot peak. We don't want to actually consume that character, so I'll peak, and if it happens to be a closing brace, what I can do is I can consume the character, because we haven't consumed it, we just peaked it. If it is, I will consume it, chars dot next, and then I will break out of this loop because we're done processing. The other case is that it will be so we consume these 4, we consume these, this is a byte, right? So the byte will be followed by a comma. So the next possible value for here, it could be a comma. So if it is a comma, then we know that we need to increment, we need to go to the next, basically. But we only go to, so the input may be that whoever was writing, they gave way too many way too many hex numbers right here, and we can't actually even process them. 0x11, that's more than 8, right? So we can't even process this many. So if that is the case, if I has already reached n, uh, in that case we should return none because the input is invalid. But if it hasn't reached n, only in that case we need to go to the next integer right here and parse it. All right, so if I is less than n minus 1, so if it hasn't reached the end of this bytes array that we created, if that is the case, only then do I consume this comma chars dot next. But if that is not the case, if we reach the end of n already, if I has reached n already, in that case, what I want to do is I want to return a none because the input is invalid. And the input is invalid. All right. After the so control will come here in the best case scenario when we have consumed this square brace. So there should be nothing after a square brace, right? So uh, the string should be empty after this. So if chars dot next, and if there is something left is sum, if there is something left in the iterator, in that case also we'll return a none because invalid input. Otherwise, since it's an option, it's returning an option, we'll return a sum of bytes. So that will parse this input to an array of bytes from where each element is basically a hexadecimal byte. All right, let's write it. Operator to extract the option. We are missing something. Yeah, we're missing a question mark right here. Huh. Okay. So that is str to vector. The only case left now is the long double. Now this long double I've left for last because it requires some custom processing for long double. So in the last video, you'll remember we changed long double from F128 to a array of bytes that is 10 bytes long because that's what CPP has. So for long double, what we will do is for long double, we want to convert it to an x87 long double, which is basically 10 bytes. So we'll write a custom code to do that. str to x87, let's say, and it takes the val star, and then like all the other cases, we are dot mapping register value of we create a long double out of it, and array yaar, okay, or invalid format. So now we need to implement this str to x87 function. Let's do that. Fn str to x87, and it takes which is basically a string slice, and it's going to return an option of an array of bytes, and that bytes array is going to be 10 bytes long. So u8 10, that's what we want to return from here. That's what we want to return from here. And okay, so now I want, for this long double, I want to support two formats. One is a hexadecimal format, and the other will be a just floating point decimal format that you see. So the hexadecimal format for it could look something like this. Let me copy an example. So this is basically 1.0 hexadecimal. If it were a decimal, so this actually converts to 1.0. You can actually even echo uh, you can say, will it work? Yeah, so it's basically 16028 1602. So this echo I think will, so this is basically equal to 1.0. If it were being parsed as a decimal, this would be equal to 1.0 as per the IEEE standard. And the other format that I want to support for it is just basically the decimal format that you see. These are the two formats I want to support right here, like basically a decimal number and then a hexadecimal format. So we'll handle both of these cases. So we can differentiate this on the basis of the first two characters. If the first two characters happen to be 0 and X, then we know uh, that we are handling the hexadecimal format. So what we'll do is, hmm, so we'll check if s dot starts with, if it starts with a 0 of X, we know we are in a hexadecimal format case. In that case, what I'll do is I'll create another helper method that will parse x87 to hex. We want to support this case because this is the only case where we won't have any precision loss. If we were to actually convert, because we don't have this data type in Rust, right? If we were writing this code in C++, we would have this data type and we could parse it into that data type, but we don't have this data type in Rust. So the data type we have in Rust is F64. So the below one format, which is actually human readable, we cannot handle that directly in Rust. We will need to convert it to an F64, and that will cause some precision loss. Some of these values will be lost in the process. Why? Because we'll be converting it to an F64, and then we'll convert it to x87 using a function that we wrote earlier in the previous video. All right. Let me show that to you. We have this do we have this str to float? No, we don't, right? So for float, what did we do was, where is float? So uh-huh, F64. Sorry, not F64 parse. The string is s dot parse, and we're going to just copy it from here, basically. Uh, Parse, and we're going to parse it to an F64, right? And since it's going to return an option of U8. So what we'll do is, so this will return an option. Okay, that will make it an option, and then I can make it into that byte of 10 by an array of 10 bytes by using the function that we created in the previous video, register value. In register value, we have a function called f64 to x87, f64 to x87, right? Huh. So this map will create that for me. Or what you can do is register value of f64 to x87, and it takes a val, and this val is going to be s dot parse into f64, like so. I think that is better. Register value of x. So what does this return? It returns u8 of. Okay, so I can create a sum out of it, option है ना? Sum of register value f64 to x87 s dot. So this s dot parse into f64 will drop some precision, and then we create an x87 format out of it, and then we wrap it in the enum, and then we wrap it in a sum, and then return. Now we need to implement this parse x87 hex function. uh let's do that. What does this say? Consider you. Is that a warning, right? That's not an error. No, that's not an error. I'll ignore that. And now we need to implement this parse x87 function. Fn parse x87 hex. It takes a stir and it returns an option of a u8 of 10 long, by array of u8s, that is 10 u8s long. So now we have an error right here, syntax error. Why? Oh, sorry. Implicitly returns empty as its body has no tail or return expression. Okay, so we need to, so this string will be starting with a 0x, so that we need to strip. All right. So the control will only come here if it is starting with n 0x. So we'll strip that. Let hex string equal to s dot strip prefix, and the strip prefix takes a prefix, and the prefix will be 0x. All right. What does this return? GD. Oh, it returns an option of stir. It returns an option of stir. So we need to unwrap it or something. Huh. Okay. So for it to be 10 bytes long, there needs to be 20 hex characters. So we should check the length of this hex string, and it should be equal to 20. If hex stir dot len not equal to 20, in that case we will return none. But if it is 20 large, in that case what we'll do is we'll create an array, let's call it bytes, and it's going to be u8, and it's going to be 10 in size, sorry 0. And so what I'll do is I will fill it with zeros, and it will be 10 large. So it will initialize the array and everything will be 0 in it. So for I in 0 to 10, we don't need this space here. Let byte stir equal to, so now we need to extract two bytes from it, so 2 bytes at a time. So for I, when I will be 0, I want to extract byte the character number 0 and character number 1, and when I is equal to 1, I want to extract character number 2 and 3. So for 1, I want to extract 2 and 3. So we are multiplying I by 2 and going up to 2. Okay, so hex stir, we have I, we'll multiply it by 2 and then we'll go up to I into 2 plus 2. What this will do is, if when I is equal to 0, this range will go from 0 to 2, and when I is equal to 1, this will go from 2 to 4 exclusive, and that will give us two characters at a time, basically. So we are extracting 2 characters from the hex string, basically. Uh-huh. To make it look cleaner, stidx, let's make it I into 2, and let up to be equal to stidx plus 2. So this can, we need to go from stidx up to basically this. So for I, when I is equal to 0, when I equal to 0, this will be equal to 0 and this will be equal to 2. When I equal to 1, this will be equal to 2, and this will be equal to 4. When I equal to 2, this will be equal to 4 and this will be equal to 6. So that's basically what we're calculating right here. We're getting two characters at a time in this byte stir, and now I want to create a U8 from this string, and this is hex in basically base 64 format. So what we'll do is U8 from stir radix and byte str, and the radix is going to be 16. So this created the byte for me. But what does it return? GD. It returns a result. So dot OK, and we'll set it into the result. So basically bytes of I equal to this, that will update the 10 bytes for different values of I. And finally, so now there is something important. This format that you are given, this format that you see right here, this is big Indian format. Big Indian format. That means that the most significant bits are written first, but when you store the values in a register, so those need to be in little Indian format, and to convert from big Indian format to little Indian format, you can just simply reverse it. So bytes dot reverse, and then sum of bytes. That's it. Is there any error? There are 10 errors. What the hell the errors? Let's see what are the errors. Huh. What are the errors? So do I need to compile it to see the errors? Oh, so I remember now. So right here we created this parse value, but we still haven't made this function return a result. That's still left. So let's do that. I guess that's the only thing left. What I'll do is I'll open a new terminal. CD OneDrive, CD desktop, CD project, RDB, ls, WSL, and right here I'll do a cargo build to see if that is the only error we are getting. Okay, what are the errors? Let's see the errors and let's fix them. Okay, so the error is okay or invalid format. So register info line number 410, it needs to have a comma after it. And this we need to return a result. F64 found result of X64. Some register value expected F64 but found a result. Okay, we need to do an OK over it. So we need to do an OK right here. So let's go into register info. Hex star byte star doesn't have a size known at compile time. Doesn't have a size known at compile time. The size for values of type str cannot be known at compilation time. The trait sized is not implemented for stir. Okay, so we need to, I think, convert it to oh yeah, it's giving us what we need to do. We need to add a, so let's go there, register info, uh, hex stir, and right here it's telling me to add an ampersand. What else? Here I need to add an expect. It's telling me what to do. It's telling me to add an expect right here after dot parse, I guess. Dot parse dot expect, and I can say basically invalid format. And somewhere I'm missing a comma after invalid format right here, I guess. Let's write this and let's do another build. Cargo clean, clear, cargo build. Let's see the errors. Bruh. Self is a reference, so the data it refers cannot be borrowed as mutable. Where is this? Process.rs, where we are doing self.handle read. Okay, so we need to make it mutable here. Okay, handle register. We need to make it mutable in handle register. Okay, let's go there. Mute, handle register write, handle register mute. Okay, needs to be mutable in handle register. So let's go to handle register. Where is handle register? Yeah, here it needs to be mutable. What else? Clear, cargo clean, cargo build. I hope it's now only that result error that we were talking about, that we need to return a result from that function. Huh, this is only that. Okay, so now let's go to this function right here. We need to return a result. Right here, we want to return a result. And basically, I just want to do that so that we know if we wrote to the user successfully or not. So for success, I'll just say stir. Just say stir. Wait a minute. There was some other error as well, right? I guess the error was that we needed to convert it to a string. Compilation time, it needed to know the size at compilation time. Was that the error? Okay, we'll see. Due to one previous error. Okay, there's only one error. That's fine. So, so if user, hmm, user bytes. So if you were to go into this write register function, this returns a pointer to a U8. And in here we are returning a null mute. So if this pointer happens to be null, I want to return an error. So if user bytes, it happens to be std ptr null mutable pointer. In that case, I will return an error saying couldn't write to user. Couldn't write register. That is fine. And what else is there? I guess we don't need this print line anymore. Let's clean it up a bit. Self dot write user. And what does what does this return? So this doesn't return anything right now. Let's go back. And what does write user? Write user is also not returning anything. So what I'll do is I'll make those functions also return a result. Let's make this write user return a result and write FPRS and write GPRS. All three of these functions should return a result as well. Here we need to return a result and it's basically str str, and instead of panicking I'll return an error. Instead of panicking I will return an error, and if everything goes fine I will return an OK of register updated, or route to user, maybe route to user. And in right here also I want to return a result of str. So and instead of panicking I want to return let's just say register updated. Let's do the same thing here as well. Instead of panicking Hoshiora fish fillet. Also, there happens to be an error right here, bug right here. This doesn't need to be actually a reference. We were giving a pointer to the stack location holding the reference. When we do this, we are giving a pointer to the stack location and not the data itself, but this function requires for it to be the data, not the pointer. And similarly here, it shouldn't be a pointer either. Let's see if it still gives that error or not. So right now we have one error. We have 29 errors. What? Cargo clean. Cargo build. Let's see what the error is. So expected found str. What? Expected error no found str. What? Let's go to the first error. So result, I want it to process.rs, but result, huh? Remove unnecessary generics. Expected is 0. Wait, is there some import issue? Is the result something else? Result. This. Where is it being used, yaar? Did I add that? Space GD. Did I add it? Yes, I added it right now, but where? We don't need that. Guys, if you imported this along with me, please don't do that. Okay. Let's try to clean and build again. So I suppose there are no errors now. So the code compiled, but it won't work. And why is that? Care to answer, I guess? It is because the user struct that we have here, the user struct that we have, the st space, where is it? fpregs, gd, st space. You see right here, it's not an array of bytes. It's an array of u32s. All right, and this xmm space is also an array of u32s and not bytes. That means that it would be in proc registers. Yes. So in proc registers, we have this write register function, right? This write register functions. So what this does is it receives a register value and it simply tries to write whatever is there in this register value at that register using the offset basically. But the register value, where is it? But the register value for long double happens to be U8, an array of U8s. but the st space is an array of u32s, so that doesn't work. So we need to have special consideration. We need to have some special consideration for the registers where the register value will be different from the format in which they are stored in the user struct. In the user struct, we have U32s, but the register value has U8s. So we'll need to somehow convert that U8s to U32s. Basically, uh, 8 fours are 32, right? So 4 bytes need to be packed together, and we need to write some code to do that. And all of this stuff, it needs to happen for only specific registers. So right now we'll do that for the FPR registers, that is basically st space. So I showed you, right? Where was it? User register info. Yeah, yeah, here you see st space. So we'll do that right here. We'll do that special changes for st space only right now. If register dot register type, for st space, the register type that we have happens to be uh, fpr. All right, so if the register type is fpr, that is not enough. We also should basically check if the register format is long double, and register dot register dot register format is register format of long double, which is true for the FPR ST space registers. If that is the case, then what we want to do is we want to pack 4 bytes into one U32. So we'll need to do some uh, basic algebra to find the actual indexes at where we need to store them. So uh, we should extract. So this val is basically register value, right? So we should extract the underlying bytes from it. So let x87 bytes equal to match val, and we match it to register value of long double, and let's say bytes. When bytes, we return bytes. If that is not the case, and we know that will always be the case because we have created the register so that this will always be the case. Otherwise, since we are returning a pointer from here, if that is not the case, I will return this stdptr null mutable pointer. That's what we will return from here. So the next thing we need to do is we want to figure out this write register. What it does is it writes the value into uh, the user struct, right, at particular offset, and that offset depends on this register. So we need to figure out the index to figure out the offset where we need to write to figure out the index of the register. So let st index equal to match register dot id. Now if that id happens to be st0, then that means our index is going to be 0. So uh, register id st0. In that case we write 0, and let's copy this, and 0 1 2 3 4 5 6 7. So we'll make it 1 2 3 4 5 6 7 6 5 4 3 2. uh, for any other id we are not going to process here. So return, that will basically never be the case. If control comes into this if case, then we will definitely match one of these IDs that we know. uh, Null mutable, and so that gives us the index of the register, basically the st register that we are trying to write to. But that index it so each st register is basically 4 u32s. If you look into the user struct that we have created, so uh, 4 u32s is 16 bytes, and those 16, so an st register is 10 bytes large, and that doesn't fit into three that fits into three registers, 12, but there is an extra byte. There are extra 4 bytes for padding. So each st register is basically 4 u32s in st space. All right. So so the index for the first st register is 0, and the index in the st space for it would be 0 for the first stack register, where this st index is 1. The first four are already occupied by this st0, so that the first st register actually starts from the fourth index. So that's why, to actually get the index for the calculating the offset, let's call that the base index, we simply need to multiply the st index by 4. All right. Now what we want to do is we want to convert uh, 10 bytes. So these bytes are basically 10 bytes, right? Long double, that is an array of 10 bytes. We want to convert them to u32s. All right. So to do that, uh, s- uh, the first two, the f- so the first two bytes, the first two u32s are basically the first 8 bytes. All right. So if we pack those first 4 bytes into a u32, that will be essentially the first u32, and then the next four into the next u32. From the third onward, we have some special handling that we need to do, because the third u32 is basically just uh, it will only be 2 bytes. The rest of the 2 bytes will be empty, and the fourth u32 will be completely empty as well. So we need to pack the first 4 bytes and then the next 4 bytes. So I'll create a loop for I in. We'll just run it 2 times, because we have 2 packs, right? Of 2 packs that are full of bytes. So 0 to 2, let u32 bytes equal to, right? We'll create u32 bytes for the first pack. So 0, 1, 2, 3, 4. We need to pack 4 in there. All right. So when I is equal to 0, we want the 0, 1, 2, 3, 1, 2, 3 index, and that can easily be got by x87 bytes I into 4. When I is equal to 0, this will also be equal to 0. All right. Uh, Semicolon. Acha, one y. One, bruh. Okay. So we can add 1 and 2 and 3 to these now. Plus 1, plus 2, plus 3. All right. Those are the 4 bytes that need to be packed together. So basically, we want to create a U32 from it, right? And we can do that by U32 from, and all of this is Little Indian format. So Little Indian of we created we converted them to Little Indian, right? By reversing the array, we converted it to Little Indian. So here we will put u32 bytes. So u32 uh, bytes from lay bytes, and we need to put this into let packed u32 equal to this, and we need to put it into the st space that I showed you in user, right? So self dot data dot I387 dot st space. All right, st space is an array, and we know base in it will go into base index plus if. When I will be 0, we will put the first u32, and then when I will be 1, we'll put the second I32. So that this will base index was the index where base index is the index for that particular register in the st space, though this will be the index of the first u32 of that register, and we can put it equal to packed u32. All right, that will this will put the first two u32s. All right, now the next u32, uh, is basically 2 bytes and then 2 zeros, because we only have 10 bytes, and if we try to cover the next u32, that will be 12 bytes. So the rest of the 2 bytes, only 2 bytes are remaining from this where is it, val x87 bytes, only 2 bytes are remaining, and we'll put it into the third u32. So what we'll do is let u32 bytes equal to uh, x87 bytes of 8, and then x87 bytes of 9, and then I told you we want 0 and then again 0. All right, and we'll convert again a packed u32 from this. Let uh, packed u32 be equal to u32 from lay bytes, and then put u32 bytes in it. This creates the u32 that we need to put it, and it is the third u32, right? So we'll put it at base index plus 2, because one is at base index, one is at the second is at base index plus 1. So the third one will go at base index plus 2, self dot data dot I dot st space of base index plus 2, and let it be equal to packed u32, and the final one will be at index plus 3, and this will basically be equal to 0. All right, so we have put all the data into the correct positions, and now we can finally return a pointer to data, because that's what we are returning from this function, right? Right register, we are returning a pointer to so we are basically returning user bytes, which is a pointer to self.data. So we want this pointer to self.data, a mutable pointer to self.data, and we can do that like so. Return we want a mutable, we want to borrow self.data as mutable self.data, and then we want to convert it to a mutable pointer, and we are basically going to be processing it as a pointer to u8s. So you can write it like so, or you can write it like so: register value as bytes, register value dot as bytes mutable, and then this. So if we go into this, so this is also basically doing the same thing, only this is also creating a mutable pointer to bytes. I think this should be it. Why are there any errors? Why are there errors? Are there errors? Syntax error, expected semicolon. So there should be a semicolon right here. What else is the error? Acha, there should not be any. It should be a comma. What else is the error? There are two more errors. Where are the errors? Where are the errors? So let's compile and see what are the errors. Cargo clean and cargo build. Okay, let's see what the errors are. Okay, so process register line 102. There should be a semicolon here before base index. Where is the base index? Alright, so there should be a semicolon right here, and that is right. So that removes the error. Does it build now? Cargo build. All right, awesome. Okay, so now we have all the code written required to write and read values from registers via the CLI. So let's try to do that. We'll do a cargo run of yes. Yes is a basic process in Linux. It just keeps on printing Y. So we are debugging that process, and now we can try to write values to it. So this is a popular value used for testing purposes, that is 0x cafe cafe, and it is basically equal to this integer. So we'll try to write this to the RSI register, and that would look like so. Register write RSI 0x cafe cafe, because I told you we'll be working in base 16 format, and I can try to read it now. Register read RSI, and that gives me the value, this value right here. So we were able to write to the RSI register and read from it correctly. So the next thing we'll try is writing to the MM0 registers, and this MM0 registers is vector format, is stored in vector formats. So we'll give it a vector and register read mm0. Let's see if it wrote it correctly or not. So if you see, when we read from the register, the first 4 bytes are written correctly, BA5E, BA11, and then rest are filled to be 0, which is fine. We can try the same thing with XMM0. Let's try to write to XMM0. We can read from XMM0, and it should have a lot more empty bytes. So it has a lot more empty bytes. That is fine. We'll try to write to the FSW register, which is a special register. I'll explain what that register does probably. Okay, so I'll do that. So let's try to write to register write FSW 0xFFF. We'll try to write this value to this. Now this it's basically accepting long double value, and try to read it. Register read FSW. So it wrote it correctly, 4095. Now let's try to write some value to the stack register. Register write st0, and we'll write a long as value of pi. And I told you in this format there will be some precision loss, and you will be able to see that. So there is going to be some precision loss when we read from it. Register read st0. So see, some precision was lost. We do not have anything after this 3 right here, but that was expected. Register write st0. Now we are going to write in a hexadecimal format, and this hexadecimal format won't cause any precision loss. The hexadecimal format. Okay, so register write st0 and this hexadecimal format, and then let's try to read it. Register read st0. So I told you it equals to 1, and yeah, it does. Those are all the tests that I basically wanted to test. All right. Uh-huh. Okay. So for long double, as I told you, we promised no precision loss when the user writes to it in hexadecimal format. If the user gives decimal format, as you see right here, there will be some precision loss. Uh, The x87 FPU register doesn't just let you write a value to a register like normal registers. You need to, so the ST registers, when you are working with the stack, you need to also write values into three other registers. So you can't simply just write value to ST0. You need to write value to FSW, FTW, and FCW as well. So the FSW, FTW, and FCW are special uh, registers. So the FTW stands for floating point tag word. The FSW basically stands for floating point status word, and FCW is the floating point control word. So what happens is when we write value to stack, we put the actual value in the ST register, and this tell we need to control the behavior of the stack. So we write the meta information about the stack, that there is one item on the stack in the FSW. The status word tells us that. All right. And we need to confirm that the data written on the stack is valid data, and that we can do by writing 1 to the FTW stack. So let me just bring in my notes and show them to you. So this is what we tested and seems to be working fine. So this is what I have. So when you're writing values to the stack registers, you can't simply just put values in the register and assume that everything will work fine. That is because there are some assembly instructions like FSTPT, FSTPT, FSAVE, FXSAVE, FXRSTOR. So these are assembly instructions. All right. And these assembly instructions expect that you not only update the value in the stack register, but also three registers alongside with it. The three registers are FSW, FTW, and FCW. All right. So when you have to update a value, when you put a new value to the into the stack, you put the actual value in the stack. So there are 7 registers, right? Then you tell uh, the FPU means basically the system that is processing these, the floating point unit. So you also need to tell the engine that is running these assembly instructions that there is now one item on the stack, and we do that by updating the FSW register. And we also need to tell it that the value that we updated into the register, it has valid data, and we can tell that by updating the FTW register. All right. All these instructions that I told you, they need to know, is there actually data on the stack? FSW tracks this. Is the data valid or garbage? FTW tracks this. And FCW tells us how the rounding should be done and precision of the float that is being stored in the register, etc. So control just tells you how to parse that value, etc. That's it. The FPU stack is circular. So when you go to 7, and then if you go beyond 7, then you will end up at ST0 again. The CPU needs to know which of these 8 slots is currently the top. The status word, that is the FSW, SW and the FSW stands for status word. The floating point status word is a 16-bit register that tracks the FPU state. This FSW register will tell you where the top of the stack is. And the FSW, so the bits 11 to 13, so it's a 16-bit register, right? So these 11, 12, 13, these 3 bits tell us the top of the stack, because 2 would be 6, so you need at least 3 bits to track 7. So uh 2 would be 4. You need at least 3 for 8. So you need at least 3 bits to tell us which of the 8 stacks is at the which is the top of the stack right now. So you need 3 bits of the status word. So the status word register is a 16-bit register, and of those, these 3 bits tell us the top of the stack. So when any of these commands need to know the top of the stack, what they do is they read the FSW register, and then they see the 11th, 12th, and 13th bit of that register, and that will tell them the what is the top of the stack. When you push a value onto a stack, the pointer decrements, it goes down. So you actually go down, you don't go up. And an empty stack starts at pointer 0, and when you put a value in it, you wrap around and reach back to 7. As I told you, the pointer decrements and it's a circular stack. Since we want to simulate a stack that has one item on it, we must manually set the top pointer bits to 7. So when you assume you have an empty stack and you want to put a value at the top of the stack, that would end up at, since an empty stack pointer is at 0, when you put, it will end up at the 7th position, right? So you will wrap around -1 decrement and you will end up at 7. So you need to update the 3 bits, 11, 12, and 13 bit of the 16 bits to tell that it is currently pointing at the 7th register. So this 1111, this 111 will tell, this 111 will be, this whole thing will be stored in the FSW register, and these 3 bits tell us what is the top of the stack right now. So, and that is not enough. If you have data in a stack register and you have the pointer to it updated as well, you still need to tell the engine that is running these commands that the CPU that the value that this stack, so this points at the seventh stack register, the value in the 7th stack register is valid or not. We need to tell the CPU that. So a 1 1, uh, so the tag word has 2 bits for every register, 16 bits total, so there are 8 stack registers and 2 bits per stack register. That would mean 16 bits total. So FTW is again a 16-bit register, and updating the 2 bits for a particular register to 1 1 means that the register is empty, and 0 0 means it has valid data. So when so if you want to update, so like you want to put a value in the 7th register, you also need to update the uh, FTW, the 2 bits of the FTW that point to the 7th register to be 0 0, because 0 0 means valid data. We want the register at index 7 are top to be valid and the other 7 registers to be empty. We set the tag word for index 7 to 0 0, because that would indicate that the data is valid, and set the rest of the indices to 1 1, right? Like so. So this is what the data in the FTW register would look like. That's all that you need to do when you update a stack register. Uh, maybe we'll write a wrapper around it, this whole process, because it's kind of tedious to remember that. So maybe we'll create a function that updates, that pushes a value onto a stack, and that helper function will do all this for us. But that's for next time. And I guess that's it for this video, and I'll see you in the next one. My bad, guys. I forgot to say. I will add all this stuff that I read out to you in the comments or description. So reach out to me if I don't add a comment for a reminder if I don't end up doing that. But most probably I will. So see you in the next one. Bye bye.